The normal extraction, Zymo, Kaijin, where you use beads to kind of bash the DNA, right? Those kind of fragment the DNA and produce roughly about 10 kb fragments. Not the ideal for paper, but too short for producing high-fi data. And the thing with peptide technology is if you have shorter fragments, yes, you're going to have the highest quality of data because the fragment is so short that the polymer is repeatedly over is multiple times. But what you are losing is the full production ability of a cell. The longer the fragments you have, you're going to produce data to the maximum capacity of the smart cell. That's the difference. So that's why we need to have high molecular weight so that we can produce the maximum output out of a smart cell. So you can imagine if you have here, we're going to do a fish today. And the fish, when I looked at the genome of a fish, it's 2.4 gigabases long. That's big. That's big. So from a smart cell that produces 30 gigs, you don't want short fragments because you're never going to hit the maximum output of the cell. And this is where it becomes tricky if you don't know. Because for instance, if you say you bring me that genome and you say I want 30 times coverage. What is 30? How do you calculate 30 times coverage from the genome? If somebody comes to you and says, this is 2.4 gigabytes, please produce 30 times coverage. How do you get the amount of data that you need to produce? You take the genome size, 2.4, you multiply it by 30. Right? By 30 times, whatever times coverage you multiply it by 30. What you get there is the amount of data you need to produce. So can you quickly do the math for me there, just to say how much data we need to produce for this genome from your phone, whatever. Let's say 2.4 multiplied by 30 times, 75 gigabases, right? Yep. That's the amount of data we need to produce. If this sample was directly from, it is from Africa BP, they come to us, we know every sample that comes to us needs a minimum of 30 times coverage. Then we will quote them for 75 gigs. So if you do extraction and we don't get high molecular weight, if we have to produce that 75 gigs over, let's say 2 smart cells or 3 smart cells, if we don't get a high molecular weight and you use your QIAGEN, you use your which is for standard extraction, you're going to end up using twice the amount of smart cell to reach that 75 gigs because what? The fragments are short, then that means the production of that cell, it's limited, it's low. So that's why we need to make sure that we extract high molecular weight so that we get fragments between 15 and 25 kb for the maximum production of the cell. Yeah. So we're going to quickly go through the workflow. No, 2.4. How much is 2.4?
72.
Yeah, whatever that number is, but it has to be 30 times coverage.
Yeah.
So if it's 1 gigabase organism, you need 30 gigs.
Okay.
You get what I'm saying? So whatever number you just multiply it by 30, and you get 30 times coverage. So which is what we can aim here for this genome. I'm not sure if it's been sequenced, but if it hasn't been sequenced, that's even great.
It hasn't been sequenced.
Yes, perfect. Because that's what we want to do as Africa BP. We don't want to replicate the stuff that has been sequenced before, right?
But the genome size is between 500 MB to 800.
800.
Yeah, the relatives are ranging between that. There's one that was being sequenced in Japan.
Okay. They're going to do something else.
Yes.
Okay, if it's like that, it's even better because that means we don't need many small cells. Yeah, we don't need many. We can do it with just one small cell or two. So we're gonna go through. So yeah, your program is gonna change a bit. This extraction is quite long. Yeah, that's been my worry. That's why I always don't include it in the practical session. But for your sake, I've been told to include it. My worry is I need to be at Kenyatta University on Friday for a talk. So I hope we can do it in time and finish so that I can move to the other side. So I'm not going to go through the technology. I've explained it yesterday, but I just want to go through the workflow that we're going to be going through. So if you look at this, so the kits that we have, it's a nanobind kit. Previously it was from a company called Seculomics. That company was bought by PetBio. It's now under PetBio. So we just brought in, it's quite expensive kit, so we just brought in a few extraction reactions. So we're going to group you guys so that you make use of those reactions adequately. We're going to do extraction. It's quite long. Hopefully we'll be able to finish, and at the very best do shearing, and then it can run overnight, so that when you come back tomorrow you can start with the actual library. Okay, it's quite long. And then the more you incubate, the more you have chance of extracting very good DNA. Now this is different because the reason why I say you need to use this kind of kits. There's one from NEB, there's one from, I'm sure there's one from somewhere else. It's because they don't use the beads to batch the DNA. They use kind of a magnetic bead. That kind of, when you extract, when you break out the cell, the DNA kind of entangles around that disc, which is what you see here. And then it has a magnet, and then when you do the purification, you wash with the buffers and everything, that magnetic substrate kind of binds to the magnetic stand that you would have put your big tube in, and then you can do washes, and at the end of the day, you're able to and then you can actually see it when you add the alcohol, it will precipitate. You can actually see the cloudy there, the strand of the DNA in the tube. So we're going to do that. Hopefully we finish today. And then the second part will be QC, we do QC just to see how much we've got. And then from there, we do the shearing. We have you will see the instruments. We came with them from South Africa. You will see the instruments in the lab. So we use what we call the megaropter. The megaropter is like a syringe kind of shearing where it takes the DNA over and over a tiny hole where it kind of cuts the DNA according to the specs that we have set on the machine, the speed actually. The higher the speed, the lesser the fragments you will get. The lower the speed, the higher the fragments you're going to get. So that's the concept. We do that, we do the shearing. There's a lot of QC step. That's one thing I can tell you. There's a lot of QC step. As much as there's a lot of QC step, that gives you an opportunity to control what you're doing. Yeah, to control what you do. That's why we are so careful with everything that goes into the paper machine. We do QCS to check that we actually got the right fragments, and then how much do we recover from the shearing, because we need to start with a certain amount of the DNA into the library. Once we do that, we run that on the tape station to see the fragment distribution. That will tell us what fragments we have, and then we do the measurements with the qubit. And then we go with what we call the smart bell prep. The smart bell prep starts with, we'll come back to this slide. The smart bell starts with the end repair. End repair basically means that, so when you shear the DNA, you don't always generate blunt ends. You have sticky ends, some lengths all over the place, right? And then the end repair and the DNA basically means it kind of fills those gaps or cuts to create blunt end. And then at the end of the once you have nice blunt ends, as you can see there, we do what we call the DNA tailing. Why would we, the DNA tailing basically, we just ligate an O and A base to the molecules, to the opposite side of the molecules. Why do we do that? Because our adapters, other than an ligate, have a T overhang. Have a T overhang. So these adapters here, this halo thing, they have a T overhang. So T and A bind together. Then you have a closed structure, which is this one. This is what we call a smart bell. Smart bell library. After we generate a smart bell, it's another QC step. You have to run the tape station to see the fragment distribution. We have to run, we have to measure on the cubit, because before the final cleanup and you have all this, there's this step. Nuclease treatment. Nuclease treatment basically it's a combination I think, of 4 or 5 enzymes. 4 or 5 enzymes in enzyme mix. Basically just trying digesting all the
Just a minute. So you are not allowed to wear lab coats. Yeah, around this. Lab coats are only for the lab, so you can just keep them nicely.
So yeah, this we can just take them nicely and then we just continue. It's a combination of enzymes. Basically, they are there to kind of digest everything that is not a complete library. Right? If there's an adapter or floating around, those enzymes will digest it. If there's a fragment floating around without adapters, those enzymes will digest it. It's like more like a cleanup step. And then just make sure that we end up with this nice complete library. And then the next step, so once we are happy with our library QC, we go to what we call 2-step. Sequencing primer annealing and polymerase binding. And then in order to able, so once we have the library, we go into the software. I'll show you. We go into the software. That actually might be problematic. I'm not sure if we'll be able to connect back to the machine back home. But okay. But anyway, that step's not going to be done. The annealing and binding, because once you do that, at the same time you need to load. So, but yeah. So the next step after we are happy with the library, with the quality of our library, we go to polymerase binding. Sequencing primer binding, annealing, and then polymerase binding. So what you see there, so you bind the two sequencing primer, you can see that, and then you anneal the sequencing primer, and then you bind the polymerase through some series of steps and pipetting dilutions. So the concentration of your library and the size of your library, when you put those things into the smart link software, run design, it will tell you how much of the sequencing primer to add and how much of the polymerase to add to that library. Okay? Based on how much you are loading into the sequencing. And then basically this is now complete, ready for sequencing. And then of course, as I mentioned yesterday, the sequencing is it's a thing of beauty really. Yeah. Once the machine starts sequencing, yeah, the polymerase, it will go into that around the molecule, but once it starts to displace the first strand, we call it the displacement mode. That's where the polymerase is at its best. That's where it's at the displacement mode. So before we run, there's a 2-hour, we call it pre-extension step, where we just allow the polymerase to go over the molecule until it gets to the stranded displacement mode. Then we start collecting data from there. So that's when the polymerase is at its best. And then, I'm sure with Illumina, if you have used Illumina before, there's a thing called overcluster, right? It's a nightmare, right? With this system, when we load, there's a thing that is kind of used to calculate, it's called adaptive loading. Whether you can load more than what's recommended, the system, once you start loading, based on the fragments and the concentration, it will calculate how much it will take to actually load 75% of the smart cell. How much it will load and at what point it should stop so that the smart cell produces the maximum data to avoid overloading. So we never worry about that. Which is the great thing. You know, when you overcluster, you go back to Illumina and they'll tell you, well, you overcluster. That means you lose your reactions, you lose your full cell. There's no such thing. The adaptive loading kind of prevents all of that. Yeah, so if we do more than one sample, and so we're doing the same fish, so we're not gonna, but we're gonna sequence one. Okay, because it's the same fish. So if you were doing different like bacteria and then doing fungi and all of those things, you're gonna have to barcode each right? So that we can load them into a single cell. Then we have two ways of barcode system. This is basically used for, it's called the smart bell adapters. So this is what you use for this type of stuff that we're going to do today, where you just ligate, like I showed you before, just ligate. It's a ligation-based adapter addition. And then on my right there, this is for your implements, your 16 years, your ITS, PCR-based barcoding step. But we're not going to do the barcoding today because it's one sample, so it's not necessary. Yeah, so we have that system at the top at the moment. It's called the SQL 2D. So if you're running a hi-fi like for this genome, yeah, if you're running for this genome, so it will run for 30 hours straight. So you have different run times based on the applications that you run. If you have amplicons, it runs for 15 hours. If you have bacteria, amplicons run for 10 hours. If you have bacteria, it runs for 15 hours. But if you have shotgun with genome, because it's whole genome based, it runs for 30 hours. If you have longer than 3 KB amplicons, it runs for 30 hours. If you have big genomes like this, it runs for 30 hours. So we're going to do that on the SQL 3E. But like I said, we are getting this machine before the end of December. This one, regardless of what you're running, if it's big genomes, you run for 24 hours. And then the difference with that one is it's sequential. If you have 4 cells, it's sequential. What the first cell finishes, and then the second one comes in, the third one comes in, the fourth. So you can end up running for straight 7 days, right? Whereas with this one, it's independent. So if you load 4 genomes all at the same time, they will finish in 24 hours. They're all finishing the stream 7. And what is nice is you can load one smart cell here, like you can load fish here. Let's say tomorrow you receive a human genome, or in the morning, or let's say you start running in the morning, and then in the afternoon you receive a human genome. You can start the library. And while this machine is running, you can open it and load the second sample. Yeah, the other side will just continue. The other side will just continue. And the nicest thing is, whether you have 1 sample, you have 4 samples, you can start the machine. You don't need to have bulk waiting of samples, so that it makes financial sense for you. Some platforms, yeah, they are big, but you can't run 1 sample. It becomes too expensive to run that 1 sample. So this way you can have only 1 genome loaded. And if you run 1 smart cell, only first reaction will be used. And it will wait for that, and then you go and tell the machine, okay, I just loaded the second sample, it will go back to the second smart cell and the second reaction. Like that, until that plate is what is used. And some, once you open the flow cell, it's used, it's more single use. That's the difference. And then, yeah, so this is the software that we used. So once you've generated the library, on that one, we go to what we call so the software is called the Smart Link. So we do 2 things with the library once we have the library. Sample setup is where it tells us how much of the annealing primer you use, how much of the polymerase you use, based on that library. Once you have that completed, the second thing is run design. Run design is basically you telling the system, look, I've added this sample on plate A1. The sample is on my 96 flow plate, it's on position A1. And this is how much concentration I've loaded. And this is how much, this is the sample in A1, I've linked it to smart cell 1. Right, so the system, once you play it around, you can see there, we have, yeah, of course you have to load the tips. You have 1, 2, 3 is where you load the tips. It uses like 5 tips, but I don't know why we have so many. Yeah. And then you have sample plate up there, you have the mixing plate, and then you have a smart cell tray too. You've got 2 positions. So like I said, smart cell tray has 4 smart cells. And then that's where you have reagent plate is basically a sequencing plate. And then this one uses the nitrogen, and then so it kind of feeds the polymerase with the nitrogen. And then you load, and then when you do the checkup, It will check out the position of your sample. Does it correspond with what you've told the machine? The smart cell, whether it expired or not. The sequencing plate, expired or not. And then there's what we call the smart web. Just to, when did you use it, the smart web can prevent evaporation. And then once all that is ready, the system already knows where to take the sample and link it to what smart cell. And if you have loaded one or more smart cell. Okay. So, as you can see, so this is an example of loading the new system. It's quite big, so it's kind of the same height as me. But the sequencing rate is it's like this. This is all the super powerful computers. So everything is happening on board. And the software it comes with the system, it's free. It's inside the software. So you basically can run this machine and do analysis from the server on your laptop. So you don't have to install those. As long as you have a compatible server, a storage server, you can link that server to your laptop. You can do it from your home, from wherever, because everything is done on the server. There's nothing that is processed on your computer. Therefore, you don't need that super powerful computer that other platforms need. So everything is processed in the computer. The demultiplexing, post the run cleanup and like hi-fi rates. So you saw the things the way you just produce more of the same reads. After you have done that, there's a step called CCS processing. That's when it takes all those reads and generate hi-fi reads. All of that happens in there. So what you get out of that machine is hi-fi reads, low file size. You can demultiplex right in there, and then just do your secondary or your tertiary analysis from wherever you are. So when you listen to presentations, others they will tell you, yes, we do produce this long read and all of that kind of things, but they never mention the computing requirements. They never mention the computing requirement. Okay, this is the smart link, basically software. And all the analysis as well. It's once you're done, you can just go back to smart link. These are the checks that you can have. So the instrument, just to check, make sure of the instrument setup, there's the latest version and all stuff like that. Sample setup, this is what we do, tell them. Once the library comes in, you can calculate annealing, binding, and cleanup reactions. And the runs, that's where we create the run design. And once that run is designed and all those kind of things, you go to data management. Data management is where you're going to see how my run performed, the run QC, run matrix, all those kind of things. The control reads, all those things you can see by looking at. This is all done on your laptop in your office, right? Because what you have, you access the machine from different locations through the server. Analysis. If you done amplicons, you can do demultiplexing from your laptop, but all of that runs through the machine. It's happening within the machine. You can perform your genome assembly, your everything. There are different pipelines that are already set up for you based on different applications. The RNA sequencing, and all of those are in the smart link software. So it's a fully packaged smart link software. So if you are interested, let's say you are running your paper from somewhere, the other supplier from everywhere else, but you are interested in using the smart link, you can go to Pepper's website, download it, and use it. Yeah, but because you don't have the machine and the server, then that's where you're going to need to consider some powerful computers for your personal usage. But if you have the machine, you just need to install the server and just make sure that you have the right network connection to your thing. And then the data analysis we will do once the run is done. So you guys, I'm sure there will be a register or someone will register with your names. Once we've run that genome, our bioinformaticists will set up the meeting with you guys so that you can have a remote, and then you just go through the assemblies, the everything, methylations with you guys remotely. And then I think that's it. You have to go to the lab. for me, the worrying part is the extraction, and hopefully it goes well. But I think we have plenty of sample if it doesn't go. Okay. Good. So you arrived a little bit late. Yeah, that's what it is. And then we have how many of you? 10. Okay. So one group will have 4 people. So 3. Oh, okay. Yeah, 3, and one will just train with me.
Just a small question. You said, just from your undergrad,
Yeah.
with the smart technology and everything, do someone still need luminaries?
Then,
Do we still need luminaries?
no, quite honest, you don't. And at some point, people that do whole exome sequencing will just need to do a whole genome sequencing.
Or genome sequencing?
There won't be need to just target specific express or what.
Okay.
That's outside the region. You don't know what's going on in that.
Okay. And another question.